Hi, thank you. Yeah, so I'm Johanna Hansen. I'm with Woods Hole, and just a forewarning, I'm not an oceanographer, so please forgive me if I'm mispronouncing something or whatnot. I'm coming from the engineering side, and so today I'm going to talk about what it takes to explore the deep ocean, what we're doing with our data sets, and how we've utilized Python to provide more introspection, and then we'll go through a couple of example problems that we see. So I'm part of the National Deep Submergence Lab, and what that is, it's a collection of a few vehicles, and we work for the NSF primarily, and provide access for scientists that want to or that need data from the deep sea. And so each of these vehicles, you may be familiar. On the top left is Alvin. That's the human submersible where scientists actually get in and dive to the bottom, and they've got robotic arms, and they can take core samples and things like that. Jason is on the bottom. That's a remotely operated vehicle, so they've got a big tether, and they hang off the back of a ship and go down to, I think, 6,500 meters. And it's a big workhorse and collects a lot of video data, coring samples, that sort of thing. And then the vehicle that I'm going to focus on today is on the top right. That's an AUV. And so what that means is it's an autonomous. We program it with a mission, and it dives down to the seafloor and runs typically a mapping operation. And for that vehicle, we haven't got much in the form of data upload, or real-time data upload, or navigation. So it's a unique problem, I think, as far as the data set's concerned. So what do we do? What do we do to actually get the data? So typically, we'll go out on a cruise, a big ship, and we'll sail out a few days offshore and spend up to 3 to 6 weeks sending the vehicles down, collecting data, and working sort of 24-hour operations with dives up to 40 hours at a time. And then we'll bring the vehicle up to the ship, recharge the batteries, and process the data really quickly, and use that information to plan another dive. So our goals are really to empower scientific users with good data that's quickly processed and available. With the autonomous vehicle, a lot of times we use it as sort of a scout. So we'll send it out and make it run over 100 kilometers or so, and make a bathy map or photos, or collect photos. And then we can use that to sort of direct where we want the ROVs to be placed, because they can't quite go as long of a range. They're not meant for driving all around. Whereas the autonomous vehicle is really good at that. We call it the lawnmower of the sea. So it's just out collecting data and working on the seafloor. And then we also want to provide science with really custom instruments to collect the data that they need. The top picture there is a new feature for Sentry. We call it the Plankzooka. So it's off the coast of the Carolinas right now, collecting plankton data from the seafloor. And so we've just strapped that on there, and it's driving around, grabbing plankton, and we're adding these sensors and also their data products to our pipeline pretty quickly. So obviously, constraints in the sea, working in the deep ocean, pressure is an obvious one. It's really expensive to build machines that are pressure tolerant to all that. So probably our development cycle's a bit slower than a lot of places. It's also pretty risky to send things down and test it. So Python has been great at sort of helping us reiterate and test pretty quickly. And the other big constraint that I see is we send typically 5 engineers out with the vehicle at a time, and less than half of those are really doing the computer processing. And so we want to automate the data task as much as possible, so to free up staff. So what kind of data do we collect? The picture on the right is a Sidescan sonar image, and so that's just an example of some of the data that needs to be stitched together, preferably within an hour or so. The data on the top left was a sort of a scouting mission. We were looking for oil seeps, and so we were able to search a large area and figure out where the seep was with this. And the bottom picture is some magnetic data. So let's look at an example of some photos. This was from a cruise that we did last year, and that we'll do again, a similar cruise this year to look at ecosystems and how they've been affected by trawling, which is where nets tend to disrupt the ecosystem. So the top picture is where you can see some actual scrape lines from the trawling fishing, I guess. And the middle image is an example of coral or some life going on. And then the bottom image is rocks, which for this cruise we didn't really care about. And so the objective was we'd collected upwards of 10,000 big images. They're about 30 megabytes apiece. And we want to figure out really quickly where the coral is, because that's what we care about. And this particular dive, we were sort of scouting for coral, and we went over a seamount and came down the other side. And so to be able to find where the coral was, we can throw this into a classifier pretty quickly and look at the texture and make a quick map of what things look like. It can be a bit of a difficult problem. The lighting and the focus can vary as the vehicle's sort of traversing the seafloor. The altitude tends to change a little bit. And so yeah, I'll just walk through what I did to get to this. I used a Gabor filter bank to classify between the different textures. As you can see, we've got some interesting differences in the texture responses here. So it was fairly successful to classify these images. I just labeled these myself. I grabbed about 400 images that were of each data type and stuck them in a folder, and was able to use a bunch of scikit-learns and scikit images feature extractors to sort of build this pipeline together. So from the huge 2048 by 4008 2672 images, I grabbed patches of 255 by 255 out of that, just to make processing easier and lighter, and also because I didn't think we needed all of that information, just for this broad view that we want to take. So I used a random forest classifier on the patches, and was able to achieve pretty good test accuracy on my sort of clean data set. On my patches that I took to train the classifier, I grabbed really good representations of each class. So you can see the red boxes were ones that I chose, and these were as illustrations of coral. And then the yellow box down on the corner was sand. And for this particular problem, I had 5 classes. And then to determine what the new images would be classified as, I would grab a handful. I think my N was maybe 5 or 6 patches from a new image that I hadn't seen before, and use patch-wise voting to determine what that image would be classified as. So here we see, this is a plot of the dive, and we're able to see the cyan color, I guess, is the scars. Those are where the trawling made an effect on the seafloor. And then we've got pieces of coral and sand in there as well. So this gave us a really quick way to determine what depths the different types of seafloor we're at. Another thing that we've used Python for is working with sonar data. So this is a new project that we've embarked on to work with MB System. So MB System is a sonar processing program produced by Dave Caress of Vimbari, and it's been super useful for a lot of the oceanographic community. But for us, it's command line, and it has a bit of a high learning curve, and so we wanted to sort of make it easier for all of our engineers to use with our pipeline. Excuse me. At the same, I'm so sorry. And at the same time, we wanted to provide a methods of introspection. So now we can actually load our we have a method of loading these the sonar responses into NumPy and actually plotting and working with developing different filters to sort of clean up our maps as well. So I want to thank the folks at WHOI, the members of my team that have been really helpful in getting a lot of this off the ground, and then also Dr. Dave Valentine, and Amy Bacco-Taylor, and Brendan Rourke, whose cruises provided a lot of the data for this. So if you'd like to work with some of the oceanographic data, we've got all of our data up on the NDSF website, and it's there. Yeah, so I think that's all I've got. Do you have any questions? Thank you.
Got plenty of time for questions.
Nope. Okay. Thank you. Sure.
Can you tell us about this plot over here on the right?
Sure. So this is a plot of some work we just did in the Gulf of Mexico, and so this is looking at the bright spots. There are actually areas where there's some brine pools, and so you can see those showing up on the multi-beam.
Did you look at all which, I guess when your classifier was failing, what was the most common, like was it mischaracterizing one as a more often?
Yeah. Okay, so that was pretty interesting. So when it fails, it typically fails, and there's some places that would look a lot like coral, even to me, when I was having actually a bit of trouble labeling it. And it would be areas where there'd be maybe some stone that had some roughness to it. And so in that respect, the texture, it wasn't actually a very good representation of what was going on. So I'd like to actually look at sort of incorporating maybe some data from the Doppler velocity log or some of the other sensors we've got there, and also using some spatial attributes that I just ignored right now. Yeah. Yes.
I'm wondering if you think from that track sample, you'd be able to make predictions of the other bathymetric data set, the rest of the area that the sample bathymetric not directly.
Certainly. I think there's a lot of opportunity for doing some additional data analysis on this, and that's definitely one of the goals I'd like to work on. Yeah. One of the constraint is typically when we're taking photo data, where we fly at a different altitude than when we're taking sonar data, and so you'd have to fly two separate missions to really lay those two on top of each other. But it's an interesting problem. Yes.
What are the differences?
Yeah. So when we're taking a photo survey, we typically fly at an altitude of 5 meters, and then our multi-beam surveys are typically about 60, 65 meters. Thank you.
Could you just tell us a little bit about what kind of core Python packages you do and all this? I heard scikit-learn.
Yeah, absolutely.
Any other big players?
Yeah, scikit-image is a huge one. I use that quite a bit, and we've started using Python sort of as a replacement for MATLAB, and we're kind of extending that. We've also, by making MB system fit into our pipeline a bit better, we've also extended that to processing Sidescan and sub-bottom data. So I've actually gotten into using OBSPy. I don't know if anyone here has contributed to that, but it's great. It's a great package. I've really enjoyed working with it. So. Also, if anyone is using MB system, the packages and sort of the wrapper, I guess, for that will be open source pretty soon here. So we're working on pushing that back to the community.
Any other questions?
Yes.
One other question. You mentioned you're using SciPy. I'm not sure but I'm curious what you use SciPy for.
Yeah, so I use it with sub-bottom data. So that's,
All right.
yep.
Sorry.
Thank you.